We're going to have some iClicker questions, and like we have been in the past, we're going to talk about resistance concepts today, and you're going to have some resistance calculations, current, voltage, resistance, very basic stuff. And then we're going to have a homework assignment for the weekend. Also, I'm going to dismiss early today, really early, so that I can work on laboratory equipment and start getting you. There is no, you guys are supposed to be doing labs in here, lab type activities. Uh, there's 33 groups of 3 people in here that we're supposed to have lab equipment for. However, there's no, they don't have a list or anything of all the lab equipment that I'm supposed to use. So I have to go and basically track down everything in this room. Nobody, the people that have taught here a few semesters already know about it, but I don't. So I'm going to spend it like half hour, 45 minutes today. And Andrew and Kendra and I are going to try. If anybody wants to stay after, you sure can, and help me fool around with the equipment. Hopefully not electrocute ourselves or anything. But we're gonna. So that's why we're going to dismiss a little bit early, so that hopefully by Monday we'll have some lab activities. All right. Now, go ahead and turn on your clicker. Hit the refresh. We're going to do alphanumeric questions. Modify the slide. Here we go. Here's your first question. I hope this is becoming familiar to you. Short answer, type in 1 or 2 letters. No, type in a letter A through H and then hit the send key. "20 seconds. Go ahead and make a count, please. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right. Let's check your answers. Yeah, pretty good. The answer here is northwest. It's basically here. As always, if there's a positive source charge, it's away from the source charge. In this case, the source charge is down the southeast. The field from that charge points to the northwest. Right, next question. And this one, type in a number and then hit the send key. I'll give you a few minutes for this one.
Double check. You have it at the proton at position 0, -2. You want us to use the 5, -2 now, right? I think you have the same.
Oh yeah, students, the preamble of the question says 0, -2. Use 5, -2. Use the diagram, and I'll modify that for the YouTube after we're done. Okay. So follow the diagram, calculate the magnitude. 79, good. That's how many answers we got last time. Excellent. All right. Can you try let's try the document can. Let's just put this on top of it. Okay, switch over to doc cam. Okay, switch out. Okay, that's good. We'll use that. Give me my calculator. Thank you. You know, Joel's right. There's any number of people flying around in those golf carts. It seems like for any reason, except for helping somebody that needs a ride. But yeah, I mean, they need. I mean, some people need them. You know, the guys that are gardening and stuff. But sometimes you see people, they don't seem to be doing anything.
I feel like they're mostly just like the people that work in the student union,
Yeah,
students, and whatever they do.
yeah. And you know who could really use one is Ray, because he has to drive around campus to different lecture halls with demonstration equipment. You know, and it's difficult for him because then he has to go. You know, he has to walk basically with the equipment on a on a cart of some kind or a dolly, and then he has to go back or get somebody to go and get it for him. It's definitely not optimal, and we don't have our own a big enough lecture hall except for this nasty 260. Actually, all this is going on the YouTube. Nice. Well, they've heard me complain about 260. They should be public knowledge, I guess. But 2 minutes. Cyrus Beckstein, are you here? Not today. Olivia phone break. Okay, she's here. Christine Campbell, where are you? Boy, your hair is a lot different now than the ID photo. I'm starting to learn these names. Rachel Dupuy. Rachel Dupuy, you're here today. Good. Were you absent Wednesday? You were? You weren't? Oh, really? Because I was calling out your name the other day and nobody responded. Were you sitting somewhere? Because I was aimed over in this direction. I know there are. Rachel Radigan across the table from you. I know her by, I know both of you by face, but you were facing away from me. And you must have been concentrating. Good. That's what I want. Jordan Enriquez, are you finished with your calculation yet? Good. Joy James, where are you today? Oh, okay. And your hair is a lot different too than your ID photos. Eric Lee, where? You're here. Matthew Martell, where are you today? Ooh, absente. Cassidy McManus. Cassidy McManus, where are you? She must be absent. Megan, I know. Mackenzie. Mackenzie Monty, are you here today? This is difficult because I can't. Nick Perez. Nick, are you here? Absent. Okay, 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. How many did you say? Not everybody voted on that. I'm not happy about that. But I am happy about your performance here. If I can actually look at it. Good. Yeah, 0.577 is the answer. And students, it, it appears that for the first time, over half the class got it right. We're getting there. Emily Meister, we're getting there. We're getting there. Emily Meister. I know. I call anybody can be called Meister. Didn't you ever hear that? Okay, X component. And again, use 5 comma negative 2 instead of what it says at the top of the page. We're already into some clicking questions. Katina. Katina. Is it Katina? You're Katina Gaskin, right? No? Where's Katina? Oh, you're Katina Gaskin. Tricked. Okay. Are you getting the answer yet? You working on your trig? All right. These guys, I gotta memorize their names. Jason, start getting an answer in, my friend. You better hustle and bustle. See this table over here, J1? I want you to go see. Hey, you guys, is this X component, is it positive or negative? Why? It's going left. All right, so you better have a negative sign, whatever else you have, better have a negative sign. Do not let me catch you napping. See, everybody's clicking now. You can hear it. Okay, good.
He's teaching me Spanish too.
Really good. Sometimes students just catch your attention for in good ways. I'm very happy about it. That's what this class is supposed to be about. You know, there's yeah, the fact that students, you know, under our guidance can learn enough to teach their group, and supposedly that's a lot more effective than me just being up here blabbing my big mouth for 90 minutes or whatever.
It seems to work.
Heidi, Heidi, Heidi Hassett. She's not paying attention. Let me walk over here. Oh, let me just brace myself here. Okay, he's good in the the old switcheroo. How you guys doing over here? Do you have your answer yet? Huh. Section summary. Very nice. Huh? Yeah, yeah, very nice. I'm giving you this. Very good. I thought that's what you're doing. Mm-hmm. Mm-hmm. It certainly does. I'm glad you're using that. That's what we started doing the same thing up with our desktop up there with our Dell. You know, I have your guys' mug shots on half the screen and the textbook in the other half of the screen. So practice names and look at problems. Oh boy. Okay.
Oh, this message.
Okay. 1 minute.
So if there was an election,
1 minute to go.
you do have to consider the direction. The charge. Y direction. Do I hear the Y direction come back? On the Y direction. I think the reason I was asking this is that's when you have like a proton and an electron on each side of the person. And you would add the fields from both. I just prefer the proton to just positive number and then the electron so then you also
10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right. Answer here is negative 0.346. Now let's take a look at some of the answers that were typed in. All right, this one's good. They forgot us. You know, actually, I'm surprised that you could put this in without a 0 in front of the decimal point. A positive number, you can't. You can't start a positive 0.346. It won't even give you the decimal point unless you have a 0 first. But I guess the minus sign permits that. All right, let's see what else we got here. Okay, now 40% of you got that one right, plus 1%, so 41%. What else? 1.602. Okay, here's the problem with the direction. That would be for something northeast, not northwest. Right? We need a negatory 0.346. 577, that's the answer to the previous problem. Come on, baby. Oh, look at this. You guys are going to have to be really careful with them. This is an equal. I'll give you this one. Come on, baby. Well, I'll give it to you when I can grade it. But you're going to have to be careful with that minus sign. Don't use the equal sign for it. Look at this one. Look at this, an underscore, which I didn't realize they had an underscore, but apparently they do. So, anyways, it looks like you guys are making progress. And actually, I'm going to analyze this problem over the weekend probably. Now, in case you didn't notice, this particular problem, I moved the proton. So this is another source charge over into the fourth quadrant. And we're keeping the same field point, 2, 2, but this one is actually built on a 3, 4, 5 triangle. I just picked a point out there, and I didn't plan this, but it works out. And that means that it's particularly easy trig. The cosine of theta is 3/5, and the sine of theta is 4/5. The tangent is 4/3, et cetera, et cetera. Now, I want you to go to multiple choice, and I'm going to give you a yes or a no question here verbally. Okay, it's not in the slides because I just thought of it as we were going through here. Now, I'm going to give this question to you verbally, and I don't want you to look at your neighbors. I mean, it's not like top secret information or anything. Well, in a way, it is. It's kind of confidential. I want you not to necessarily look at what your neighbor's doing. Just try to be private for a few minutes. Usually, I want you guys to, coordinate and talk things over. But this one, I just want you to answer as you see fit. And my question is this. Do you feel like your group of 3 is helpful for you? A for yes, B for no. Do you feel like your group of 3 at your table is helpful for you? Don't talk it over. Just answer whatever you think.
You have to open the poll.
Oh, okay, go ahead. A for yes, B for no. And either one is fine. Ten seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Now, okay, I'd like your attention now. Thank you for answering that question. I'm waiting. All right. I want to explain why I asked that question. This class, sometimes students register for this class without really knowing why it's in this room and why we have computers and everything. Okay, fellas, you can return your seat. Um, this is called the Studio Physics classroom. Studio Physics. I don't know why they call it studio, but that's what they call it. It is designed for you to work in groups of 3. And the idea is that you will learn more efficiently by me doing a little bit of lecturing, a little bit of demonstrating, and a little bit of eye clicking with you, and you guys interacting with the people in your group a lot. Now, for those of you that have had me in the lecture hall, you know that I encourage that, but it's kind of hard in a lecture hall to get seated together so you can all look at the same paper and everything like that. But here it's supposed to be better. All right. Now that is why we are here. This is not supposed to be a regular lecture. And the reason for that is because a regular lecture, they've done research out the wazoo. And they have found that a class like this, students, they might not feel like they're doing a lot of learning, but they actually do a lot of learning in a class like this. Versus other types of teaching, including lecture, and what they found is that lecture is the least efficient method for students to learn. But what do we do the most at UCF? Lectures, right? So ideally, the physics department, if it was up to me, I'd have half the number of you guys, half the number of tables in here, and a lot more open space in here. You guys are crammed in like sardines here, and I don't like it that much. We need some room up here, some room to roam. Like these 2 tables alone, if we could get these, much as I love you guys as students, if we if if we could, put you guys out in the hall or something, or make the room a little bit bigger and move it out there in the hall that way, then we'd have plenty of room up here because there's demonstrations that you can do in front of a group that would, and actually surrounded by students, that would be really cool. But we just can't do them. And so, and the other point I want to mention to you is in this studio mode, which is why you have to sign up for this section and then the section right after it, section 5 and 6, you're also supposed to be doing labs. And that's why you're going to be dismissed early today. Now, I know you guys get broken hearts every Friday when I dismiss early if I can. But in this particular case, we absolutely have to get going with the lab component. So we're going to do some emergency exploration in here after I dismiss you guys. But anyways, that's the theory of this classroom. All right. And I encourage you, as I do in lecture hall, and I encourage you here while we're clicking most of the time, to coordinate and kibitz and give advice, wise advice, hopefully to your neighbors, your group members. I do it in the lecture hall, I do it here. And in the lecture hall, we can't wander around, with the LAs and the GTA, but here we can. And so that also makes it, any kind of interaction that you have with an expert like me or like Andrew or like Kendra increases the amount of learning. Any interaction that you can have with your classmates it won't be the same as interacting with an expert. You'll be interacting with a peer, but that will help you learn. It's the principle that, as they used to say, iron sharpens iron. So peer to peer, you're going to help each other learn. You may not realize it, but you will. And you've probably, sometimes you help your friend and you feel good. Yeah, I know that one. You know, and you never know what's going to happen. But uh, so so the emphasis is on discussion among you guys, and that is why I try to encourage you to read the textbook before coming to class. Because we're not, if you haven't figured it out, we're not taking a page by page voyage through the textbook this semester. I'm peppering you with questions, and we're talking about them as we go, and then we're discussing concepts. But it's not like me, it's not like me down in room 260 blabbing my big mouth for 90 minutes twice a week, or stuff like that, and nagging everybody. I mean, I do plenty of nagging about homework up here, so that's all right. But I'm not supposed to be blabbing my big mouth for 90 minutes straight up here, or it's almost an hour, 2 hours now for this class. Now, let's get back to multiple choice questions. And let's talk about chapter 20.2. First one, the concept of electrical resistance. There's a picture of George Ohm. 20 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, very good. Um, yeah, most of you got that one right. C is the correct answer. I think 90%. You know where I got that? My explanation to you a few minutes ago about interacting with an expert, interacting with your peers. The more you do that, the more you learn. You know where I got that? Terminator 2. With Arnold. No, Arnold's he says, I'm a learning machine. I'm a cyborg. I have neural network processor. I am a learning machine. The more interaction I have with humans, the more I learn. But that's not a robot. Like a lot of these superhero movies, they're not really about, some guy. They're usually about us. And that is definitely about us. The more interaction I have with humans, and I'm looking around the room here at humans, yeah, I think pretty much everybody in here is a, well, maybe there's a one or two space aliens in here. I don't know, but most of you guys, the more interaction you have with humans, the more you're going to learn. And in the context of physics, that's why that's how I explain it that way. Now, the people that developed this studio physics process, they weren't thinking of Arnold in Terminator 2, but I was. All right, second question, or next question, I should say. Now go ahead and write down these four equations because I'm going to have comments about each of them. And only one of them is correct. 30 seconds starting right now. Fifteen seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. Uh, whoa. Check out these. We got some splaining to do. All right, but that's all right. I've already anticipated that. And I know that, let me try to make this a little bit smaller here. So the correct answer is this one. And here's why. If you multiply I, cross multiply I, current I, to the right hand side, you get delta V equals I alpha. All right, so that's a proportionality statement. So this is the correct answer here. And and basically what it means is, in colloquial terms, the more voltage, the more current. You want a lot of current? Get some big batteries. Put it that way. All right? If you don't need much current, small batteries are fine. Right? Now, let's take a look at option C. This one is inversely, the current is in, and this is false, because what it says is that the current is inversely proportional to delta V. All right? And so that one's out, because the whole idea is that they're proportional, not inversely proportional. Inversely proportional means something in the denominator on the other side. Proportional means something in the numerator on the other side, and there's no denominator, just a multiplicative factor, which is what we have for B. Now, because that is the case, C is inversely proportional. This one up here is also inversely proportional. And why is that? Well, if you divide both sides by delta V, you get alpha over delta V, which is equation C. Now, A, B, and C were the three variants. And let's see what we have here. Well, it's good. You guys, a majority, no, I should say a plurality, 41% chose B. And the others were 30% and 30%, 24, 24, and 33. So more of you voted for B than for A or C. Now this one down here at the bottom, that's an equation, but they're additive. You would say current and delta V are additive. If you had that in your mind, that current and voltage are additive, you'd write a sentence like that. But it's not true. They're different units. And so you can't really add them together. That would be, you know why that's wrong? Adding apples and oranges. Remember how your mom always said, or your seventh grade teacher, don't add apples and oranges. That's why this is wrong. Okay? So just don't do it. Anyways, B is the correct answer. All right, next question. Metric unit of resistance, the ohm. Twenty seconds. This one should be like bing. 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, let's see what you guys. Oh, nice. You guys are correct. Now, for this one, the colloquial phrase is, for every amp of current, I need this many volts in my voltage source. That's kind of what if you look up the resistance and it says 7 ohms of resistance, that means that you need 7 volts for every amp of current that you want to push through the circuit at that point anyways. All right. So that's kind of the colloquial meaning of an ohm, symbolized with Greek letter capital omega. Right. And here's the version of Ohm's equation. That's the one that I remember, V equals IR, or delta V equals IR. And if you can remember that, you can figure out your units of resistance, volts per amp. Get R by itself, it's delta V over I. And that's the constant of proportionality that we mentioned earlier, et cetera, et cetera. Okay, next question. One can compare a conducting wire to A, B, C, D, or E. Is that a cool thunderstorm or what? It's somewhere out in Montana, eastern Montana. I've seen storms like that down in the, driving across the Everglades. Like that, yeah. Yeah, that's not strong enough to become a tornado, but the same circulation and downdrafts and updrafts and stuff, yeah, that's, 10, 20 miles further down, that thing might turn into a tornado. I've never actually seen a tornado, but I've seen a thunderstorm that was even more disastrous looking than that. And I later, yeah, the street lights turned on in the town where it was about 9 in the morning, and all of a sudden the sky just got black, and you could see this cloud, and it had like a bump underneath it, like that, reaching almost down to the ground. And the street lights turned on, and then it started raining like crazy. And then I later heard that storm about 10 miles further to the southeast or to the northeast, I guess, turned into a tornado. Yeah, twister. Yeah, yeah. Florida's not as bad as like Kansas and Montana and stuff. Okay, 5 seconds. 5, 4, 3, 2, 1. Everybody's clicked. Let's check your answers. What? Some of you typed in D, even though I put a picture of a thunderstorm on there. Well, that's good because D is the correct answer. Wait a minute. Uh-oh, I did. You know what? I shouldn't have said that because now I see now a few of you did vote for C, but no, a conducting wire. And you know what? In this analogy, a water pipe, you know what voltage is like? Water pressure. And current, electrical current, is like gallons per second through the pipe. All right, let's go to another question. One can compare a conducting wire to a water pipe? Yes. Resistance can be compared to this property of the water pipe. This is a figure 2 from chapter 20.2. Read this one carefully. Twenty seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. The answer, yeah, you guys got this one mostly right. It's water flowing in a pipe. A few of you voted for B, but B is not right because flowing without obstruction, that's like flowing without resistance. And if you have a resistor in the circuit, yeah, you compare it to water flowing in a pipe filled with gravel or something like that. Did you ever see that demonstration like on the internet where a science teacher takes a big glass jar and then fills it with marbles, little glass marbles, and or gravel, and then he says, "Is this jar full?" And the students say, "Yeah, it's full." And then he proceeds to fill it with sand, and the sand goes all in between the marbles and the gravel pebbles. And then he says, "Okay, now is it full?" And a bunch of students raise their hand, yes. But he says, "Oh yeah." And then he fills it with water, and then it's full because water is a fluid, not a particle. And water will fill like a fluid. It will fill all the intervening spaces. But even then, you got little air pockets of air clinging to each grain of sand. So if you had high pressure water, you could do it. Fill it even more. But that's the same thing here. A pipe with a lot of resistance or a wire with a lot of resistance would be like a pipe filled with bigger pebbles. And a pipe with really big resistance would be like a pipe filled with sand. Yeah, you can get water through it, but it's tough. And so it's much slower. So high resistance, low current for the same amount of water pressure. So, all right, now let's do another question. A resistor can symbolize sometimes we put in that symbol R with a squiggly just to symbolize a complex device. But what is it about the device that leads us to calling it a resistance, kind of a generic, or being able to replace it with a symbol for a generic resistance? Ten seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, let's check. Yeah, pretty good. Um, correct answer is A. Um, this is not too controversial, but a few of you optioned out D, the on-off switch. I heard some people talking about that. No, you know what the on-off switch is? A transistor, a semiconductor, and that's got resistance and no resistance, depending, or lower resistance. It switches from a conductor to an insulator, depending on the currents that you've got flowing through it. So that's more like and that is an on-off switch. We make our all the digital stuff in your phone and computers and everything. It's all digitals. So zillions of little on-off switches talking to each other in an electronic circuit. But it's not a resistor that does it. It's a transistor. Reverses the flow of current. No. C is nobody optioned C. Generates more energy over time. I'm glad to see that. The thing that provides energy to the system is the battery or whatever voltage source you may have, like an electrical generator or a transformer or something like that. Question. What is your name again? Jenna what? Hold on a second. Let me just verify that here. I'm looking at mug shots. Come on, no, I don't want, it took me all the way to the bottom here. Yeah, okay, you verify. Okay, your question. No, I'm just trying to learn names, that's all.
Scenario where you would use a resistor. Does that make sense?
Every electrical device, machine, circuit, even the wire has a little bit of resistance per meter, per centimeter, per millimeter.
Is there anything
Everything electrical, the only exception to that is what we call a superconductor, which is made of certain metals taken to a very, very low temperature. And at that very, very low temperature, their resistance goes to zero, zap. And so whatever current that would be a pipe without gravel in it. The water just flows in, it doesn't lose any energy as it goes through. But barring that, and we don't have any household superconducting devices, not yet. We're working on it.
So why would you want to like release energy in a way that you can just
Why would you want to waste energy?
kind of wasting all of your energy?
Well, let me ask you this. Do you have a car? You do? Okay. Is it fairly nice or is it a beater? It's got AC in it, right?
Yeah.
Okay. Okay. Now, why do you turn the AC on? Right, because it's hot. You burn it. If you don't turn on the AC, you got to roll down the windows, and then you're still hot. You just get a little breeze. That runs by electricity, my dear. And so every resistance, that air conditioner has an equivalent resistance. It's a big device, but it puts a resistance on the circuit. And if you do you live in an apartment or a house or campus? You live in a house. Do you pay your own light bill? The the okay. If you live in a house, the power company, at least up in Seminole County where I live, Duke Energy, they have a program where they have a switch where they can turn your air conditioner off under times of peak or 15 minutes per hour during times of peak. And that's because air conditioners are a huge source of work that dissipates electrical circuit energy in the course of cooling you off, right? You know what the other big ones are? Water heater and pool pump. And they have, depending on the power company, they'll have a little box in your garage or something that they can transmit by, I don't know, cell phone or radio, turn off your stuff. It's never happened to me where I live, but they have, I mean, they have it, and I've got it in my house. So yeah, everything that we use that has electricity, you can think, like the screen up here. That the screen is providing light, and so the current is doing a little bit of work in that projector. Not a whole lot, not like an air conditioner, but I mean, see the vents on it? Look up there. You see those vents? That's because that machine gets hot. So you got to have little fans. Your computer. Most of the stuff that's dissipated, no, I should say that. Most devices, all devices are going to generate a little bit of heat, sometimes a lot, right? Now, air conditioner, that's what they're supposed to do. Okay, and they cool off the inside of your house and reject heat to the outside air. Refrigerators, you ever notice that? The bottom of, or the size of a refrigerator, they have a fan in there, right? To cool off the cooling coils. They have a compressor that has to work, and it compresses the freon, and the freon goes through these coils, and they warm up the inside of they take warmth from the inside of the refrigerator to the coils. The coils expand, and then that heat is exhausted through the fan system, like at the bottom of the fridge. So if your air conditioner fails and you say, that's all right, I'll just open up my refrigerator. That'll at least cool off the kitchen. No way, because you're exhausting a little bit of heat for every degree of coolness that your refrigerator and the freezer attains. So everything electrical that is doing something useful it can be replaced by or will have an equivalent resistance that some electrical engineer is going to want to know, before he puts it on, because they have to know, the household current is a certain voltage rating, right? And so you have to have the right circuit breakers or fuses in there if you're going to draw a certain amount. And air conditioners draw a lot of, what else draws a lot of current? Washers and dryers, apparently. And so they have to have their own separate circuits and stuff like that. But yeah, so everything, uh, Jenna, everything electrical is going to waste a little bit of energy doing work for you to keep you cool and everything else. All right, let's do a numeric calculation. Oh, let me get this thing closed. All right, so hit the refresh key. Now this is our calculation. Ohm's law calculation, and this is actually from the very end of chapter 20.2. So if you have the chapter on the screen, you can read this very problem. Here it is. Type it into one significant figure. It's going to be 0.0 something, a bunch of zeros. And Andrew and Kendra, you guys can walk around now. Oh, let me start the question. So this one's going to be numeric. So just type in a number and then hit the send key. Kendra, did Joel get it correct? Did Joel get it? Very quickly. No, just give me zeros and one significant figure. So, yeah, you don't have to use scientific notation for this. How do I, why is this doing this? I was trying to scroll this. Where's my clicker?
This mouse is not very good.
Is that why? Because it's,
Yeah. It's on. I think it's on the wood, so it's not picking up the laser very well.
because it was skipping all over the place here. I couldn't get it to scroll.
Yeah, I think it's just,
Now it's scrolled better.
I don't know if we put it on like paper, it could be better.
Yeah, that might be better. Yeah, this tabletop's probably pretty greasy and this has got a little more bite to it. 2 minutes. Notice I didn't have to use my notes today. Means we're making progress.
Strong. Like, I don't know how anyone without those is okay.
With these glasses. Wow.
Yeah. Like, if the person takes them off and get out, how are they seeing?
They must have taken an exam and just been so woozy that they just kind of stumbled out to their car and they're still home.
Yeah, I had my glasses and I kept getting a headache, so I went to the eye doctor like 2 weeks ago, and I was like, yo, I can't read anything. I have a headache every time. They're like, well, this is why. And they put the old prescription on me, and I was like, everything's blurry, and then they put these on me, and I was like, but I can't read.
How much did you pay for those?
I've got two pairs for like $60.
Where
There.
I've been thinking about getting some glasses myself. These ones are just $2 specials from Walmart.
Yeah, I'm on my computer and doing homework like all the time, so reading
Yeah,
is like what I do.
yeah. 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right. Can you switch me over to DocCam, please? Okay, my wonderful students. Here are my notes. And notice I didn't have to go to my notes for the um, electric field calculation today. Nice. You guys are learning. All right, now this one, I just want to go over the basic calculation here. Okay, so V is equal to IR. Very easy. And what are we trying to figure out? The I. Okay, so I is equal to V over R, which is, in this one, the V is 200 kilovolts. So that's 200 times 10 to the 3 volts divided by 1 times 10 to the 9. So I'll just write 10 to the 9 ohms. All right, so the result is going to be amperes of current. So let's just do it on the calculator real quick here. Okay, I think you can see that. Let me bring this in a little bit. All right. So 200 times 10 to the 3, I'll just write in non-scientific, scientific notation. Okay, so there's 200,000 divided by 1 times 10 to the 9. Answer 0.0002. Anybody else verify that?
Yes.
All right. You want to switch me over to laptop, please? Okay. So there's your answer. Now we're going to dismiss now and try to do some lab equipment. Continue your reading through chapter 20 and start reading a little, skimming chapter 21. And I'll see you on Monday. And hopefully Monday we'll have a lab of some kind fixed up.